Okay, folks, we're going to finish up Chapter 9 here today. This is 9.3, Limiting Reactants and Percent Yields. Today, we're going to look at a possible mixture of equations, and we're going to see, let's just say, for instance, okay, I'm going to mix a couple things together here. Here's a beaker of a substance. We're going to call this substance, substance A, and we're going to call this substance, substance B, and we're going to put them together. It does not matter what these are at the moment, and we're going to get a certain set of substance that we're going to call A, B, right? Actually, we're going to make A, B a different color. Let's make A, B blue. Okay, A, B is blue. So, here's our B, here's our A. We mix them together, we get A, B, right? Well, that's all fine and dandy, but most of the time when I do a chemical reaction, I don't have perfect amounts of A and B. I don't have perfect amounts of these chemicals. So a lot of times one chemical is going to be used up while the other one is left over. It's like if you're baking cookies, right? You might use all the chocolate chips you have, but you still have some flour left in the fridge. You could make more cookies, but you already ran out of chocolate chips, so you can't. So maybe in most chemical reactions, you're going to have something left. And let's just say in this case, I'm going to have just a little bit of A left. It didn't all get used up. It's still in the beaker. It's not reacting anymore because the B is gone to react with it, but it has not been all used up. So that's where the idea of limiting reactants is. Which chemical am I going to run out of first? Okay? Maybe the best way to think about this is just very classic limiting reactant metaphor, and that's if I'm building a sandwich. Okay? My formula for the sandwich is going to be 2 bread, so 2 slices of bread, plus 3 meat, and how about 1 cheese? And that's going to give me 1 sandwich. Good with that? I think that's a pretty tasty sandwich. Okay, how many pieces of bread do I have? Well, let's do exactly what the book says in their example, and we'll have 20 slices of bread, 3 meat, there's not 3, about 24, and 1 cheese. So if I just look at each of these individually and I look at the bread, okay, well, if I had 20 slices of bread, I could probably make, well, I know for a fact I can make 10 sandwiches. If I had 23 slices of meat, okay, 24 divided by 3, because I need 3 for each sandwich, I can make 8. And if I had 1 slice of cheese, well, that'd be 24, excuse me, I have 12 slices of cheese. If I had 12 slices of cheese, I could make 12 sandwiches, okay? Well, I'm going to run out of one of these first, right? Well, which one do I run out of first? The one that's less. I would make 8 sandwiches, and then I'd still have pieces of bread left, and I'd still have cheese left. I couldn't make any more sandwiches. I'd still have those ingredients, but I couldn't make those sandwiches anymore, so they would be left over. This is exactly what's happening in a lot of chemical equations, where I'm running out of an ingredient first, I'm running out of a part of the chemical equation, and now I can no longer continue the reaction. Okay, so we're going to be focusing on what is left over, which one is the limiting reactant, and kind of being able to use this in a chemical equation. Okay, so let's look at a basic equation. The book gives us this equation, and I think it's a good problem, so we're going to take it as well. Let's start here. It's going to be nitrogen gas plus hydrogen gas is going to give us NH3. Let's balance this thing out. I'm going to need a 2 here and a 3 here. Okay, so there's my balanced part. Now, I'm going to have a certain amount of nitrogen and a certain amount of hydrogen, and I want to figure out which of these is the limiting reactant. Which one do I run out of first? Okay, so let's just say for nitrogen, I have 2.5 times 10 to the 4th grams. So you guys never like that. Let's just say we're just going to make it really simple. 250 grams of nitrogen, and for hydrogen, I have, we'll say 500 grams of hydrogen. Okay, so I can do the stoichiometry, which with each one of these, and in doing the stoichiometry for each one of these, let me move that down a little bit. And doing the stoichiometry for each one of these, I can figure out how much of this NH3 I can produce. So let's just kind of relook or look at the stoichiometry for each of these. This is what we did last chapter. So I have 250 grams of nitrogen. Okay. Well, I need to convert this grams of nitrogen to moles of nitrogen. So my first step is actually it'd be 28.02 because I have two of these. So 28.02 grams of nitrogen are 1 mole of nitrogen. And where do I get that 28.2? Well, I took 14.01 times 2. 14.01 is the molar mass of nitrogen, and I took it times 2 because there's 2 molecules in it. Okay, so now I'm at moles of nitrogen. I want to get to this. I want to see how many moles of this I can produce. So what's my ratio? Well, I got nitrogen up here. These labels are going to cancel out. I've got moles of nitrogen, and I want to get there. So moles of nitrogen needs to go on the bottom here. That'd be 1 mole of nitrogen to 2 moles of NH3. And then all I need to do is convert this moles of NH3 to grams of NH3. So 1 mole of NH3, well, let's see here, 14.01 plus 3 times 1.01. So that's 3.03. So I would say it's 17.04 grams. Okay? And in doing this, if I do the math for this, I would get 250 times 2 times 17.04 plus, or excuse me, oh my gosh, that's going to be 80, and I'm going to divide all of that by 28.02 because that's what I have on the bottom, and I get 304.07 grams of NH3. Okay, now do the same thing on this, same thing I did over here, but just do it for hydrogen this time. So hydrogen has a molar mass of 2.02 grams for every H2 molecule, or mole. Okay? And my ratio here is 3 moles of H2 to 2 moles of NH3. And I know that 1 mole of NH3 equals 17.04 grams. That was for nitrogen. So let's do this. 500 right there times 2 times 17.04. And I'm going to divide it by 2.02 times 3, and that's it. So the next one's 1. It's, whoa, that's a lot. I'm going to get, is that right? Holy smokes. Yep, that's right. I'm going to get 2811.88 grams of NH3. Okay? That's how much NH3 I would produce if hydrogen was all by itself. So which one do I run out of first? Well, that's pretty simple. This one, the nitrogen, I would only produce 304 grams, where in the hydrogen, I would produce 2,811 grams. Okay? So my limiting reactant in this case is the nitrogen. It's what I run out of first with. So after you do the stoichiometry for each of these, you just simply pick which one has the less number of grams for the product, and then you know, okay, this one is clearly our limiting reactant because I would run out of this one first. Okay? Okay, let's do another one here. Here's the formula that we're going to be working with. We'll say NH3 plus CuO yields N2 plus, I want more room because I have to balance it, N2 plus Cu plus H2O. Big formula here. Let's just balance this thing out real quick, hopefully quick. 2 nitrogens there. I've means I got 6 there, which means I get 3 right here, 3 right here, and a 3 right here. And I think that'll work perfect for the balance. Okay, so let's just see how many of each product we have. We'll say that we have 18.1 grams of NH3. So that product, or that reactant, I'm sorry, these are what we're looking at here. We want to find out which one's limiting. And I have 90.4 grams of Cu. Oh, okay. So which one's my limiting reactant? Which one, or let's just say how much product can I get? I guess that's probably the best way to start off with this. How much product, how much nitrogen can I get from this reaction? Okay, so if I have this much of the reactants, how much nitrogen do I get? All right, so let's just tackle this. I have to do the stoichiometry for each one of these. Okay, I'm going to do this really quick here. 18.1 gram of NH3. Okay, convert from grams, go to moles. So grams got to be on the bottom. From the last thing that I did, I said 17.04 was the molar mass of that. So 17.04 grams of NH3 give you 1 mole of NH3. Okay, my ratio says that in the formula I have 2 moles of NH3. And I'm trying to get to nitrogen for every 1 mole of nitrogen. Okay, now moles of nitrogen has to be on the bottom. I'm just trying to pair these up, right? These labels are always the same. How much does 1 mole of nitrogen weigh? Because I want to figure out how many grams of this I can have. Nitrogen is 14.01 times 2 is going to be 28.02. Okay, I solved this problem. Just doing the math here. So it's 18.01, 18.1. Why is it 18? Oh, 18.1 times 28.02. Okay, that gives me 507.162. So I'm going to divide that by 17.04 times 2. And that gives me 14.88. So I could get from this amount, I could get 14.88 grams of N2. Okay, so now all I need to do is do the same thing for copper oxide here. I'm just going to erase this so I can keep all my have more room to work. I got that number written down right there. So here we go, 90.4 grams of CuO. What's the molar mass of copper oxide? Oh, this ought to be interesting. Copper is 63.55, and I'm going to add that to 16. So that gives me the molar mass of copper oxide, in this case copper 2 oxide, is 79.55 grams, will equal 1 mole. My balanced equation says I have 3 moles of copper oxide for every 1 mole of nitrogen. And I know that 1 mole of nitrogen equals 28.02. Okay, so here we go, add all this stuff together. Or times it all together, 90.4 times 28.202. And I'm going to divide that all by 79.55 times 3 times 1, which gives me 10.614 grams of copper oxide. Which one is smallest? Well, not copper oxide. I want grams of nitrogen. Which one is smallest? Well, very clearly, this is our smaller one. So which one do we run out of first? Well, we run out of copper oxide first, and this is all of the nitrogen that we could produce. Okay, so this is limited reactants, looking at which one we run out of first and how we determine which one we run out of first. That's the only video for today. This video is going to be split into 2. So the next video we'll talk about percent yield and theoretical yield, which will be probably about 5 or 6 minutes at all, or is all. Okay, so this is limited reactant, and that is it. We're done. That's the worst way to end a video ever. I bet you're all just okay. Goodbye.